Greetings to you all, dear students. Welcome back. Today we are going to deal with a topic called Applications of chi-square distribution, which is a part of our unit titled Testing of Hypothesis. We shall first talk about what is a chi-square variate, and then we will go ahead with two applications of chi-square distribution, which shall be elaborately explained and shown in certain number of problems. Let's begin. We are all aware that a random variable x with say mean mu and variance sigma square, which is following the normal law, is called a normal variate and is expressed as x, which is a random variable, follows normal distribution, which is represented by n, with mean mu and variance sigma square. So if x follows normal distribution with mean mu and variance sigma square, then the variable z, which is denoted by x minus mu by sigma, is termed as a standard normal variate, which shall have the mean as 0 and variance 1. This also we have seen in normal distribution. So in this case, z follows normal distribution with mean 0 and variance 1. Now, when we are talking about chi-square variate, why are we deviating to normal variate? You may all think. The square of the normal variate is nothing but the chi-square variate. So that's the reason why we talked about z. So if you take the square of z, which is x minus mu by sigma the whole square, that is a chi-square variate, and it has follows 1 degrees of freedom. It has 1 degrees of freedom. So in general, if we extend this to any number of independent normal variates, say we have xi, where I varies from 1, 2, 3, x1, x2, x3, etc. They are all n independent normal variates with mean, say mu1, mu2, etc. Variance sigma 1 square, sigma 2 square, etc. Then chi-square variate is defined to be the variable chi-square is nothing but the summation of all zi squares, or the summation of xi minus mu I by sigma I the whole square. And chi-square is said to be a chi-square variate. Notation is this. It is a chi-square variate with n degrees of freedom. Since here we are talking about n variables. So when you're talking about one variable, the degrees of freedom is just 1. This variate follows the probability distribution, which is called the chi-square distribution. Our motto in this video is only to discuss the applications of this distribution and not go into the depth of the depth of this distribution. So we shall just restrict our learning here only to the applications of this distribution. So let's see what are they in my next slide. There are plenty of applications, but we are focusing on main two of them, which is to test the goodness of fit and to test the independence of attributes. These are the two applications we are discussing in this video. Now, what shall we mean by goodness of fit is it's a very powerful test for testing the significance of the discrepancy between theory and experiment. So, in short, if we have to explain, it is to test if there is any significant difference between the experimental data and the theoretical data. It's called the chi-square test for goodness of fit, and it's again given by Carl Pearson in the year 1900. So this test enables us to know if the deviation between the experiment and the theory is only by chance, or is it really due to the inadequacy of the theory to fit into the observed data. So it's going to give us a clarity as to whether the experiment or the theory both are supporting each other. So if they are supporting, if the theory supports the experiment or the experiment supports the theory. Moving forward, to test the independence of attributes, that's the second application. So here, when we are discussing about the independence of two types of attributes. So the compatibility of the observed and the expected frequencies has to be tested with respect to the independence of these two attributes. So we are going to test whether the two attributes which are under consideration, say I take them to be A and B, are they independent or not? And for that, because we shall be using two attributes and the data pertaining to the two attributes, we shall use a two-way table which would be termed as a contingency table. We shall discuss about this in detail when we come to the second application. So to start with, let us first look at the first application, which is the chi-square test for goodness of fit, and that is only going to check whether there is a significant difference between the experimental values and the theoretical values. Let's elaborate this further in the coming slides. Let's begin with the first application, which is testing of goodness of fit. Let's assume that OIs represent the set of observed or experimental frequencies, and EIs, where I varies from 1 to n, represents the corresponding set of theoretical frequencies. Then the Karl-Pearson chi-square, it follows the chi-square distribution with n minus 1 degrees of freedom given by this particular formula. So it is the summation where I running from 1 to n, OI mean minus EI the whole square divided by EI. OIs are the observations, observed values, EIs are the expected value. So the difference of the two, square of it, divided by the expected value. The summation of all the n values together gives you the value of chi-square. It must be noted that the summation of the observed value should be always equal to the summation of the expected values. So this is the test statistic that we have to check on, with the condition that we sigma OI and sigma EI must coincide. So the working rule goes this way. We first define the null and alternate hypothesis, define the desired level of significance, then calculate the value of chi-square using the summation. And if the calculated value is less than the table value, so we have to see the chi-square table value at n minus 1 degrees of freedom, compare it with the calculated value for this formula, and if the calculated value is less than the table value, then we accept the null hypothesis, else we reject it or accept the alternative hypothesis. Let's proceed and apply these in certain problems. Before we start with problem 1, this is the chi-square table which will give us the table value for the respective degrees of freedom. The degrees of freedom are given from 1 to 60, and we have various, the rows which you see here, it is 0.99, which means it is 0.01 is the level of significance. So this is the various level of significance we are discussing. It could depend on the problem where the level of significance is given to us. By default, we have taken 5%, so it will be 0.05. So we are interested in this particular column for these respective degrees of freedom pertaining to the problem that we are doing. So let's start with problem 1 now. The first problem reads the following. The following data gives the number of accidents that occur in a junction during the working days of a week. Test whether the accidents are uniformly distributed over the week. So we are given a table where on each particular day, starting from Monday to Saturday, the number of accidents that have occurred in a particular junction are mentioned to us. Based on this data, are we in a position to conclude that accidents occur uniformly over the week? Is the question asked. So, are we ensuring or saying from this data, can we judge if there is a uniform distribution of the accidents over this 6-day week? So this is what we have to test. So naturally, based on our null hypothesis, we shall say that accidents are uniformly distributed. Yes, they are uniformly distributed over the week. So it does not depend on the day of the week, but you should have the same uniform distribution is what our H naught quotes. And the alternative will be that accidents are not uniformly distributed. The level of significance by default we take as 5%. Now, when I say they are uniformly distributed, I need to first note what is the total number of accidents that we are talking about. So that when I take up, it's coming to 90. And over a period of how many days are we distributing it? So it is 6 days. So if I want to know the uniform number of accidents that can occur per day, we'll have to divide the total number of accidents by the total number of days, and that gives me 15. So my expected number of accidents per day is 15. So this is my expected number, whereas this is my observed values. So if I take the observed to be 15, the expected to be 15, then we shall construct the table and evaluate the test statistic. So I hope the framing of expected number is our job in every problem. So when I call it uniformly distributed, that expected number of accidents is nothing but the total number of accidents divided by the total number of days, and that will give me the expected number per day. So keeping the observed values and the expected values ready, let us go ahead to construct the table. So I rewrite OI as the observed values. This is what is given in the question. Expected values is EI, which we have assumed now by dividing the total number of accidents by the total number of days. That is common. It's 15 throughout. So I take the difference, then square that difference value, divide each value by 15 because that's the EI value, and I take the total of this last column, which is sigma OI minus EI the whole square by EI, as 2.01. Look at the degrees of freedom that I have. It is n minus 1. The total number of values that I am given is 6. So 6 minus 1 at 5 degrees of freedom for 0.05, the last but one column. If you note in the table, it is 11.07. So I find that the calculated value is less than the table value. So according to my result, H naught is accepted, which means that accidents are distributed uniformly over the week. So we have made a conclusion for this particular problem. Let's do a similar one in this next slide. The second problem is similar to the first one. The number of demands for a particular spare part in a shop was found vary from day to day. In a sample study, the following information was obtained. Test whether the demand depends on the day of the week. It's similar to the previous one. There it was accident, here it is demand. So as we did, quickly we can go through. The demand does not depend on the day of the week is our null hypothesis. And the alternate hypothesis is demand depends on the day of the week. We calculate the total demand divided by the total number of days, 6, and that's 120. So that's uniformly distributed. So the expected number of accidents is 120. It is demand here. The expected number of demands that we have per day is 120 each. So these are the observed values, these are the expected values, and then we can frame the table as we explained earlier. So OI values are given to us. Expected value is 120 on every day. The differences, square of the differences, these divided by each EI, that is 16 divided by 120, 25 divided by 120, and so on. The total calculated value is 1.68, whereas the table value for 5 degrees of freedom is 11.07. Calculated value is less than the table value, so H naught is accepted. So that means the demand does not depend on the day of the week. So that's how we have planned out and we have concluded the result. Let's look at problem number 3. Theory predicts that the proportion of rice cultivation in 4 zones A, B, C, and D is 9 is to 3 is to 3 is to 1. In an experiment, out of 1600 tons of rice, 882, 313, 287, and 118 tons were from the 4 zones respectively. So, does the experiment support theory? So we have a theoretical prediction that these four zones, the yield of rice cultivation is in this ratio. And experimentally, we have taken 1600 tons of rice and we have seen that these four zones give so many tons of rice. Now we have to check whether the experiment that we have done correlates with or supports the theory. So naturally, our H naught would mean yes, the experiment supports theory. H1 experiment does not support theory. So these are the four observed values given to us. And the total tons of rice is 1600. So what is the expected is what we have to calculate. This is the observed. So what we expect that the proportion of rice cultivation is in this ratio. So suppose I talk about zone A, I have 9 parts out of the total 16 parts. That is the proportion of rice cultivation in zone A. So how do I calculate the expected proportion in rice cultivation in zone A will be 9 divided by the total, which is 16, multiplied by the total tons, which is 1600. So 900 tons is the expected proportion of rice cultivation, out of which we have now seen through an experiment it is 882. The second one is 3 divided by 16 multiplied by 1600. So it becomes 300 is the expected, out of which we have observed is 313. Similarly, the third zone also gives me 300 and the fourth zone gives me 100. So these are the expected values and these are the observed values. And once the expected is known, it is just the table construction and comparison with the table value. So you see, we have the observed values. We have written down the expected values in the same order. We have taken the difference, squared them, divided each of them by the respective EI, and the total we get is 4.72. We have total number of values is 4, the degrees of freedom is 3, and from the table we will note that it is 7.81. You can check. We find that the calculated value is less than the table value, so H naught is accepted, which means the experiment supports the theory. So experiment is in line with the theoretical prediction that is made. So this is how the analysis is being done using chi-square distribution. Let's read problem number 4. The following data shows defective articles produced by 4 machines. Does the data indicate significant difference in the performance of the machines? So let's read the data. We are given 4 machines A, B, C, D. Also the production time in hours. So machine A is running for 1 hour, machine B for 1 hour, C for 2 hours, D for 3 hours. And the number of defectives that each machine is producing in the time of running. So it means machine A is producing 12 defectives in defective articles in 1 hour, machine B 30 defective articles in 1 hour, machine C 63 defective articles in 2 hours, and so on. So since we are asked to check whether there is a significant difference in the performance, we declare that H naught there is no significant difference in the performance of the machines, and H1 to be there is significant difference in the performance of the machines. So we take the level of significance to be 5% as always. But kindly note, to frame the expected number of defectives, we should first calculate all the total number of defectives. Now when I add them, I guess it should be 203. And here when I add them, it will be 7 hours, meaning that when these 4 machines are put to work, they produce 203 defectives in 7 hours. But each machine is working for different timings. So it's working for 1 hour, B is working for 1 hour, C is working for 2 hours, and D is working for 3 hours. So if I want to find the expected number of defectives, then this will mean Consider the proportion of the number of defectives. See, the total number of defectives 203 in 7 hours. Then in 1 hour it is 203 by 7. Correct? So A machine A is 203 divided by 7 will be the proportion of defectives. And how many hours is it running? It's only running for 1 hour. So you multiply that proportion of defectives by 1. That will give me the expected number of defectives. The same way, 203 divided by 7 into 1 again for B also. 203 by 7 into, C is now running for 2 hours. So we must consider for 2 hours what is the number of defectives, expected number. So it will be the proportion of the number of defectives multiplied by 2. And finally for D it will be 203 divided by 203 divided by 7 into 3. So you calculate these values, that will give you the expected number of defectives by each of the machine, in which case we have taken the proportion to be common. So there is a commonality and hence can be compared. So this slide shows exactly what I explained to you now. Total number of defectives when we add it is giving me 203. Total production time is 7 hours. So when you calculate the expected number of defectives by each of the machines, so you get the proportion multiplied by 1, which is 29, and here also 29, here it's 58, and here it is 87, because it depends on the number of hours each machine is put to work. So now we have found the expected values. Time for the table next. So we have now written the observed values, expected values, as we found in the earlier slide, and proceeded in the similar manner to get 11.83 to be our calculated value. And when you compare it with the 3 degrees of freedom table value, I find that calculated value is greater than the table value. So null hypothesis is rejected, meaning the alternative hypothesis is accepted. So there is significant difference in the performance of the 4 machines. So this is the conclusion that we make. The important aspect in these problems is how to find out the expected values. So I hope you're all understanding as we are going problem by problem. We'll do one more problem for the final understanding. Let's do one more problem before we wind up this particular application. The following data represents the monthly sales of a certain departmental stores in a leap year. Examine if there's any seasonality in the sales. So he has given the observed values of sales in a supermarket in leap year, meaning that there are 366 days. So what we mean by saying is there any seasonality in the sales is, does the sale depend on the seasons? So we have totally 12 months in a year with various seasons. So we need to check, and we are given 12 values here. If you can note, we have 12 values, one for every month, and we will have to check whether monthly the sales differ or not. So our null hypothesis will be, certainly there is no seasonality in the sales. H1 will mean there is seasonality in sales, and let us check with 5% level of significance which of our hypothesis is true. So we have the total sales that we have observed values of all the 12 months is 73,200. Total number of days in a leap year is 366. So the expected sales per day. So 366 days, you're having 73,200 to be the sales. So per day is 200. Now, when we are calculating the expected sales per month, there are some months which have 31 days, some months which have 30 days, and February has 29 days. So we shall calculate the expected sales in the months of January, March, May, July, August, October, and December, which have 31 days, multiplied by the expected sales per day. So 6,200 will be the expected sales in these months per month. Similarly, in the months of April, June, September, and November, where we have 30 days, we have 6,000 exactly 6,000 sales. And then expected sales in February, which is 29 days, would be say 5,800 would be the expected sales. So now we have calculated the expected sales in all the 12 months. Observed is already given to us. Now let's construct the table. So the observed values given in the problem and the expected values as we have just found based on the months that we have. Note that the total of O and E must be the same. Then the difference, square of the differences divided by EI, the value that we get is 38.91. We shall now compare it with the table value. Now we are given 12 months, so 12 minus 1, 11 degrees of freedom. Let's see what is the expected value and we shall compare it with the calculated value. We find that the table value for 11 degrees of freedom is 19.68, whereas the calculated value is 38. So the calculated value is greater than the table value, so we are rejecting H naught. So that will mean that H1 is accepted. So our conclusion is there is seasonality in sales. So based on the given data, this is the conclusion that we make. So this is our first application of chi-square distribution called the chi-square test for goodness of fit. Now, as we studied another one application which talks about independence of attributes, we shall do that in our next video. So we shall stop this video with these 5 problems giving insight into the test of goodness of fit, where the experimental data and the theoretical data, the supporting each other, is tested by using this particular analysis, and we have used the chi-square table to compare the table value with the calculated value and make concrete conclusions. I hope the 5 problems were comfortable for understanding. You can attempt a few more questions seeing any one of the statistical books around you, and we shall discuss about the next application of chi-square distribution, which is the independence of attributes, in my next video. So goodbye for now.